Hello everyone, my name is Luca Tortorelli and I'm a postdoc at the University Observatory in Munich. And in this talk, I would like to present the work that myself and collaborators listed here are carrying out in the context of developing an accurate galaxy population model based on stellar population synthesis for the forward modeling of stage 4 galaxy surveys. We are living in the golden era for extracting cosmological information from the large-scale structure distribution, thanks to existing and upcoming photometric and spectroscopic galaxy surveys that will revolutionize our understanding of the universe and of the galaxy population in it. We already had some examples in this direction with DESI that found that the dark energy might not be as constant as previously thought, or Kidd's legacy, who seemingly solved the S8 tension between early and late cosmological probes. New unprecedented constraints will come from stage 4 photometric surveys such as Euclid and LSST that will employ galaxy clustering and weak lensing as probe of the large-scale structures. These surveys are going to measure positions and shapes for billions of galaxies, moving our error budget from a statistics-dominated era to a systematics-dominated era. Therefore, to fully exploit this wealth of information, it is necessary to have an accurate assessment of survey incompletenesses, selection effects on galaxies, and biases on measurements of their properties. For a probe like weak lensing, there are many systematics going on, and here you see, for instance, like a non-comprehensive list. Among them, the one where I focus most of my work deals with the problem of accurately estimating galaxy redshift distributions. Indeed, the ability of this probe to constrain key cosmological parameters such as S8 or omega m is highly sensitive to the uncertainties in the redshift distributions of source galaxies, especially the mean redshift. For this reason, stage 4 experiments have set very stringent requirements on the mean and scatter of the tomographic redshift distributions, which need to be known at a per mille level in a year 10 analysis. There are a number of reasons why we are still not able to reach such a precision on the redshift distribution estimates. And if you want to know more in detail, I suggest you to read the Newman and Grun review. But basically, this has to do with the lack of performance of traditional photo-Z algorithms, even in idealized conditions, and incomplete coverage of the color space spanned by the spectroscopic samples with which we calibrate the color redshift relations. Indeed, existing samples of spectroscopic redshift may systematically miss some populations of objects, leading to biased color redshift relation, and correcting for this missed coverage requires a careful understanding of the underlying galaxy population, since the latter sets an informative prior on the redshift of a photometrically selected galaxies. The forward modeling of photometric and spectroscopic galaxy surveys is a powerful approach with which one can tackle both the problem of accurate galaxy redshift distribution estimates and the characterization of the galaxy population underlying the observation of a survey. This methodology involves constructing a detailed end-to-end model of a galaxy survey, which includes a realistic galaxy population model, a model for the galaxy spectral energy distributions, a mapping of the intrinsic properties and fluxes to the observed ones by means of image and spectra simulated, and informative observed data against which to compare and constrain the model. By forward modeling all the relevant observational and instrumental effects and calibrating model parameters using, for instance, simulation-based inference, galaxy redshift distributions constructed from observed data can be replaced by the one that have been accurately determined via simulations in a cosmological analysis. Modeling the galaxy population is possibly the most important ingredient of this approach. In a series of work that span many years, we have developed and constrained with increasingly informative data a phenomenological model for the galaxy population called GalSBI. This model was publicly released in a paper led by Silvan Fischbacher, where we build the simulated redshift distributions for HSC data in the cosmos field, an aspect that I'll come back to later. If you want to know more about this phenomenological model, please have a look at Silvan's talk. To reach the requirements of stage 4 surveys, we need to go beyond a phenomenological description of the galaxy population. Developing a realistic galaxy population model based on physical properties, the use of stellar population synthesis is crucial for the success of our modeling stage 4 galaxy surveys. Such a model allows for leveraging information for more constraining dataset, such as low redshift samples, deep fields, or spectroscopic dataset pre-selected through photometry, and transfer that information to the fainter magnitude limited samples targeted by upcoming surveys. This enables a more flexible extrapolation, whereby sampling physical properties from physically motivated priors, one can construct higher redshift analogues of galaxies observed at low redshift, so fainter and younger versions that retain physical consistency. This capability is a direct consequence of using stellar population synthesis, which allows for the generation of realistic galaxy SCDs across cosmic time by explicitly modeling the contribution of stars, gas, dust, and AGN. Moreover, the integration of this stellar population synthesis based forward modeling with the image and spectra simulator places us in a unique position of being able to characterize the selection function of a survey as function of physical properties, instrumental configuration, target selection, and observant conditions. However, one cannot naively take any stellar population synthesis code or use whatever stellar population synthesis library, because the choices of the parameter of the stellar population components affect the galaxy colors up to the magnitude level. And since the galaxy colors are the ones used to assign a galaxy to a redshift bin for weak lensing and galaxy clustering studies, as well as to estimate the redshift distribution of a bin via the color redshift relation, studying the impact of the choices of the stellar population parameters and components on SPS-based forward modeling is of crucial importance. And one can see an example on the left, for instance, on how, for a single galaxy with fixed physical properties, simply changing one single description, like the IMF or the dust attenuation, can dramatically move a galaxy position in the color magnitude space. And this is also testified by a recent work by Belsted and Robotham that showed the dramatic changes in the stellar mass estimates up to 0.5 dex when we change the stellar population prescription used to model a galaxy SCD. This was the focus of a work that Jimmy McCullough, Daniel Grun, and I published last year, where we showed for a fixed population of galaxies how their sum-based tomographic distributions were changing when varying one single stellar population component prescriptions, leaving all the other fixed. We found that the prescriptions change the redshift distributions beyond the requirements stage by stage 4 surveys, and that any effort that aims at using stellar population synthesis based forward modeling of galaxy surveys as a method to obtain precise redshift distribution for stage 4 cosmological parameters must consider the required constraints on galaxy SCD from observations. And here, for example, in this box, you see the dramatic shift in tomographic bins induced by changing the dust attenuation prescriptions. The lessons learned from this work and the necessity to move away from phenomenological models towards more physically oriented models motivated us to develop the stellar population synthesis version of GalSBI, called GalSBI-SPS. GalSBI-SPS allows us to extend the properties drawn by GalSBI by sampling stellar masses, star formation histories, gas phase metallicity, dust parameters, velocity dispersion, gas ionization, and morphological quantities, and generate galaxy SCDs by means of the stellar population synthesis code prospect. As in the phenomenological version of our model, in GalSBI-SPS, galaxies are drawn from two overlapping populations of blue and red galaxies. But this time, the starting point of our sampling is the stellar mass function, from which we jointly draw galaxy redshift and formed masses. These are then used to model galaxy star formation history with a skewed truncated normal distributions, whose estimate for the parameters have been obtained by modeling GAMA and DEVILS data. All the other physical properties that are drawn for this model are conditioned on the sample value of stellar masses, redshift, and star formation history to to create a comprehensive simulated galaxy catalog that contains not just the luminosity, magnitudes, and sizes of galaxies, but also their physical properties. The paper is on arXiv, so you can scan the QR code here and check it out. The galaxy population model is definitely a crucial ingredient, but it's not the only ingredient to successfully forward model and galaxy survey. In order to apply the same analysis steps and selection cuts on both data and simulations, we need image and spectra simulator that produce a realistic simulated equivalent of real data. Last December, together with GalSBI, we also publicly released the ultra-fast image generator that is seemingly integrated in GalSBI, such that one can generate realistic galaxy catalogs and the equivalent image with, for instance, Hyper-Suprime Cam characteristics, with a speed that is comparable to running source extractor on said image. Having an input galaxy catalog and the equivalent image means that you can run exactly the same analysis pipeline on both data and simulations, but with the advantage of knowing the ground truth of the galaxy physical properties. We develop not just the image simulator, but also a realistic spectral simulator called USpec. This simulator has been designed to simulate fiber-based galaxy spectra, for instance, those of Foremost and DESI, and we are gonna soon published a paper describing this simulator and integrated inside the GalSBI framework. The GalSBI framework is publicly available. You can scan the QR code to have a look at the actual code on GitLab, or simply pip install it, such that with a few lines of code, one can generate a galaxy catalog and its corresponding image with an HSC-like setup. The last ingredient that you need to successfully forward model a survey is a way to jointly constrain your model parameter by comparing your simulated properties against the observations. In order to efficiently explore the space of possible parameter values for our model, we accelerated the image simulation and the source extraction with an emulator. There is a combination of a detection classifier that tells us which galaxy is detected on the image and a conditional normalizing flow that maps the input properties of this detected image to the observed one that would be basically output by source extractor, thereby speeding up the whole pipeline by up to a factor of 10. Additionally, we are also developing a neural network that would emulate the magnitude computation from expensive SPS runs from Prospect. By using simulation-based inference, one can compute an approximate posterior distributions of the model parameter by minimizing the distance between the real data and the main realization of the simulated galaxy catalog, for instance, the mean of the magnitude distributions. And here, on the right side, you see an example of our latest simulation-based inference run on HSC data and the resulting posterior distributions. Having calibrated the model, one can do different studies using the posterior predictions. First of all, one can check whether the distributions of sizes, magnitudes, and colors agree between the data and observations. One can study the intrinsic relations between the galaxy physical properties, such as the stellar mass formation rate, the stellar mass size relation, or the luminosity function and the stellar mass functions of your galaxy samples. One other important study that our methodology enable is the ability to characterize the redshift success of surveys like DESI and Foremost. For instance, in DESI, in a master thesis led by Zhixiao Qin, we are training a neural network to predict from real DESI spectra the redshift confidence, such that when applied to realistic simulated data, we can characterize the redshift confidence as a function of physical and observational properties. In the context of Foremost, instead, one can characterize the selection function of a survey like 4C3R2 before the survey is actually conducted by replicating exactly all the steps that went into creating the target catalog of the survey and predicting, based on the simulation, what is the redshift success of the survey as a function of physical and observational properties. But most importantly, and this is the reason why the approach was developed in the first place, the posterior distributions provide redshift distributions that can replace the real ones in a cosmological analysis. Here you can see an example from the GalSBI paper where we compare the forward model N of Z with the same ones from Cosmos Photo Z. These N of Zs have been obtained by simulating HSE images in the Cosmos field. They agree at less than a sigma for a stage 3 setup, both with the observations, both in the full distributions and in the tomographic setup. While for a stage 4 setup, the full distributions differs by a 1.5 sigma, while the tomographic distributions still show some tension with the data. A gap that we aim to fill using a physically motivated galaxy population model trained on photometric and spectroscopic data. To conclude, in this talk, I've presented the GalSBI forward modeling framework and its stellar population synthesis-based model, with which we aim at reaching the required accuracy on the NR set for stage 4 surveys by constraining the model parameters on photometric and spectroscopic data. GalSBI is publicly available, and you can download it, install it, and generate catalogs, images, and soon spectra. These redshift distributions will then be used in a cosmological analysis that involves precursor data, such as HSC, and in the future for an LSST cosmological analysis. Thank you very much for your attention.